Hi everyone, I'm Santiago Velasco Forero and I would like to present to you my article called Fixed Point Ledger for Geodesic Morphological Operations, which is a collaborative work with my master student Ayub Rim and my colleague Jesus Angulo. So this paper addresses the use of a classical image processing operator called morphological reconstruction in the framework of neural networks. We studied the Jacobian of the morphological reconstruction in terms of fixed points and Bayesian attraction of the transformation. In addition, we present two problems to illustrate the merits of our proposition. So what is a morphological reconstruction? So that is an operator with two inputs and one output. So we have a small animation here that we want to show the result of the transformation with an input F and G. So this morphological reconstruction transforms the image G according to the image F. Usually F is called the market. So the mathematical definition is the iteration of this elementary operator, that is the dilation of F pixel Y minimum the image G. So this elementary operator is applied until it idempotent. So in the video we already finished we already see the result. So some points are important. So this transformation have no parameters. So this operator has a nice geometrical interpretation. So we can see that this here. So we have as output some of the components of the G that are the components that are touched by F. So we preserve clearly the contour of the image in G. So that can be implemented in deep learning code as PyTorch TensorFlow by the dynamic contour flow, and the definition is pretty general because it can be applied to 1D, 2D, 3D image in general. So the first motivation of this paper was to understand how the gradient flows through this geodesic transformation, and for that we studied its Jacobian metrics. So in the example that we show to illustrate our findings, we use a 1D representation, but as I said before, the interpretation is similar in 2D or 3D images. So we have in blue F, in green G, and our reconstruction is the image in red, the line in red. So we can note that the reconstruction outputs contain values corresponding to the image G or flat zones that are point without gradient. I mean, it's completely flat. So in the paper we have all the details, but the conclusion was that if we consider the Jacobian matrix with respect to F, it contains only ones and zeros, and it has ones on the diagonal if if f the xi is a fixed point of the reconstruction. So that is the point where the reconstruction is equal to the value of the marker f, which is represented here for the 3 blue points. Additionally, it has of diagonal values equal to 1 in ij if xj belongs to the basin of attraction of xi. So that is represented with the small lines in blue. So that is important because it's a clearly geometrical interpretation of what is the Jacobian. So to understand the gradients, we can see the columns of this Jacobian. So we can easily conclude that the gradient pass through some local maximums of f, and the gradient value would be proportional to the cardinal of the basin of the attraction. So similarly, if we analyze the Jacobian metrics with respect to the image G, to have the similar interpretation, but with respect to the some local minimum of G, and its Bayesian abstraction. So to explain the interest of using this layer in classical deep learning framework, we compare two convolutional two CNNs, with the difference that the second one, our proposition, use a morphological reconstruction layer at the end. So it is can see as the CNN is predicting the marker, I mean the image that is used to select some contour of the image. And it's important to note that both networks have exactly the same number of parameters. So the tags we have used to compare them is the estimation of geometric attributes on binary image composed by shapes, triangles, squares, and so on, of random size. We have used 4 attributes: the area, the perimeter, the area of the bounding box, and the eccentricity. So we have generate more of 1,000 random image with the random position of the shapes and random sizes, and we have trained models to predict these 4 values per shapes. So an example of this ground truth is the first column presented, first row presented here, and the value is normalized between 0 and 1 using the maximum and minimum value of the entire generated database. So we have performed 10 repetitions of the training by changing the initialization using a traditional protocol to train a CNN. The details are in the paper, and we show in here for the 4 attributes we want to learn the learning curve on the validation dataset for a classical CNN in dot points, and in lines our proposition using reconstruction at the end of the network. So in all the observed cases there was an improvement by using the reconstruction, but more important than have only a quantitative evaluation is we have look of the results of the CNN. It does not predict an homogeneous value per shape. That is normal because we are using convolutions, and this problem is solved by the model with reconstruction. So the CNN is basically predicting a marker, that is the first row, and the reconstruction is doing this homogeneous value on the inside the shape. So one important point is the prediction is done by the maximum value of the marker G inside of the shape. So the quantitative analysis shows a significant improvement for all the 4 problem studies. A second example of application is image denoising to perform after image classification. So our object is to compare the generalization power of pre-training network in the noise syntax for different levels of types of noise and application to different domains. Accordingly, we settle on a complicated case where only one noise level is used during training, only one kind of database. So this CNN is used as pre-training model for the noising, and its output is used in a supervised classification model. So in all our experiments, we use as database for the noising the NNIST database. So the blue lines represent a baseline where a CNN is training for classification, only classification, on image with a Gaussian noise of 0.1 standard deviation and 0 mean. So that is the blue line. Of course, when the noise level increase, that is the x-axis, the performance decrease. A natural way to elevate this problem is to include different noise levels, that is denoted here at CNN augmentation. These noise are only included in the classification part. So the augmentation is done between with 0 mean and standard deviation between 0 and 0.2. The results are shown in orange lines. So another way to improve the performance is to add a CNN before the classification to perform the denoising. This is the one I'm training only on MNIST that is presented in green line. And if the classification network is used trained with augmentation, we have the red one. So we have these four baseline models, and we compare our alternative proposal that is use a CNN to train to learn only a single value per image, that is value h, and using a morphological reconstruction, this is our proposition, using as marker f minus the value h, that is, and reconstruction on f. So this known in classical image processing books as the H-max transform. So the results are presented in purple line, exactly this model. And if the second network is training with augmentation, we obtain the brown lines with a performance far superior than the other models. So we have more result with the other kind of noise and performing the classification on a different database that the one used to learn the noisy network. And in most of the scenarios were modeled using morphological reconstruction as less as the noiser perform better than the baseline models. So to conclude, we propose and study the use of morphological reconstruction as a ledger in the context of CNN. For more details and more experiments, I invite you to see the article and the code available online.